we went to predict survival from the Titanic data set, as we did before. So I load tidy models, the tidyverse. I load my data here. I set my seed for the random number generator so that my results are reproducible. And I split my data into training data and into testing data. At least I establish the rule here. It's not the splitting itself. I establish the rule, and strata is survived. So I want to make sure that percentage-wise, I have as many survivors in the test data set than in the training data set. I have a recipe here. The recipe is quite simple. It uses the training data and establishes here a mutate step that shifts our survived. Our survived is a value of 1 for survival, 0 for non-survival. It's just a dummy variable. I save it as a factor, which is still a dummy variable, but internally in R, it's saved differently. I do the same thing with my sex variable. I run it, so it's already done for the training data. I kind of squeeze out the training data from the recipe. The command is called juice. I apply the same recipe to my testing data according to the splitting rule I established earlier. And I save the splitting rule in the variable split 85. And I have my testing data. And the nice thing with tidy models is a lot of things repeat. We don't have to learn things newly. So to run a random forest in tidy models, the command is called RandomForest. Okay, I can find that from the documentation. Like always, I have to say, what is the mode? Is it regression or is it classification? I'm predicting here ones and zeros. It's classification. And I have to chain here with the chain command, the pipe command, to the command set engine. I always have to do that too. And I use the R package RandomForest. There's an alternative. It's called Ranger. It produces almost the same results. And then lastly, I apply it with fit, my model. And first, the variable I want to predict is survived. Then the separator comes here, which is just a tilde. And then I would have a list of all the other variables that I use for the prediction. But I'm lazy. I want to use all the variables, and we can take a look at the training data set here. So I want to use all these variables. I want to use sex. I want to use age. I want to use the class, the siblings, the parents to predict variables survive. That's basically the message here. I do that, and I'm done. I mean, I think the default is about 200 trees. In that short of the time, my random forest model is done. My trees, all my 200 trees exist. The only thing is I have to use it for prediction. So my model is called model RandomForest. And again, that's how I called it. You can call it differently. I use the model here to get a confusion matrix. Well, the first thing I have to do, I have to get predictions. So I use the predict command for the model RandomForest that would go in here after piping. And the new data set is data test. Then I bind the results from the prediction to the test data. And now I tell the confusion matrix command where the results are. Let me get this off here. This is not the confusion matrix, just a preliminary result, but I want to show it to you. After I did this here, see, here are my predictions. And here are my survivors, so I can see this is a right prediction, a right prediction. Here's a wrong prediction. I predicted survival. Unfortunately, the 6th person died. The 7th person, I predicted survival. The person died. I predicted death, and the person died. So I guess you get the message here. And if I have that, then I can generate a confusion matrix very easily. I just have to say, where do you find the truth? It's in the column survived. You saw that. Whereas the estimate, it's in the column that is called dot predict class. Again, I told you, you don't use special characters in variable names, although R supports it. R itself does it, but the thing is, they use it because they would hope that you have not used a variable with a similar name. Okay, here's my prediction. I print my confusion matrix, and it looks pretty good. Look, from the people who died, the truth is 0. 49 were predicted as dying, and only 5 were predicted as survivors. From the people who survived, only 5 people were predicted falsely as being dead, but 29 records were predicted correctly. So the correct predictions are 49 plus 29. And if I calculate the ratio of this, the correct predictions overall, I just have to add these numbers all together. R does that for us, calculates the rate here, the accuracy rate, and it's 88%. That is pretty good. 88% precision with my random forest here. And how fast was it? 200 decision trees under it. Even when I run my test data, I run my records about 110, I think I had. 88 I had, sorry. 88 records. I ran each records to each of the 200 decision trees. I got a prediction for each of the record decision trees. I take the majority, and that's a prediction for the first record. Then I do that with the second, with the third, and so on until the 88th. That is a lot of work. It goes very fast. We can also see, if we look at sensitivity and specificity, I'm getting better here, that the positive class, and that's always the first class that is in the confusion matrix, and that was dying, so it's a little bit sad to say the positive class is dying, but that's how it is here. So I was better in predicting the positive class of dying. So I was better predicting the people who died than I was in predicting the survivors. But the rates are 90 and 85%. That's very, very strong. In the following demo, we want to tune 2 parameters. The parameters are the minimum amount of records that are required to do a new split. We will try 10 and 30. And the number of variables that are considered randomly at each split. And we will try 2 and 3. Here's what I want to do. For the variables, remember we had 5 variables. K was 5. And we say we should use at each split not all variables, but the square root out of 5. That would be either 2 or 3. So my idea is, okay, why don't we try 2 and 3 for the variables we are allowed to be present at each split. I also said we want to we want to limit the numbers in our terminal nodes. If the number is, let's say, smaller than 10, in a node, we are not allowed to split it further. It becomes an end node, a terminal node. We could also change this rule and say, well, now we don't want to have 10, we want to have 30. So I want to try both scenarios, this one and this one. Well, that means I'm working with 4 models. My minimum n can be either 10 or 30. My splitting variables that I try can be 2 or 3. So if I have 10 as my minimum number in my terminal node and I allow 2 variables for the splitting rule, I end up with this model here. If I have 10 for the 10 splitting rule, but I allow 3 variables, I get this model here. And I think you get the idea. If I have 30 variables, 30 records in my terminal node, but I allow 2, I get this one here, and I get this one here. So my goal here is actually, I want to compare 4 models. I start with model 1, and I want to see what is the best model depending on the accuracy of the random forest. So I start with model 1, and you would say, okay, how do I do this? How do I see how accurate it is? Again, the first idea would probably just use the test data set. No, we can't do that. The test data set is taboo. The test data set can only be used to see how the final model is, but we're still trying to get better models here. So this one cannot be used. So what we could do is, and just look at the first one here. These are our training data. They're always the same training data. These are our training data here. These are all the training data, but we have put them in 5 different buckets. We call them folds. And the black one, I don't use it to develop my decision trees. I only use these ones. These 4 ones are my training data. And then I use the one I didn't use to establish how good the model is. And I could stop there. The only problem is, well, maybe I just got lucky because I used fold 1 as my assessment fold. Assessment fold is the one that I use to assess the quality, the black one. So what we do is we rotate through all of them, and I show you how. And I strongly recommend when you review that in the PowerPoint, do it in presentation mode, because then you get the story. So this is our first trial. I use the folds 2 to 5. I put them all together for training, and fold 1 I use for assessment. I get the accuracy from that. Then, and I'm still in model 1, I use fold 2 for assessment, and for the training data, I pour my folds 1, 3, 4, and 5 into one bucket. And I do that. Here is 3 is my assessment fold. The rest are used for training. 4 is my assessment fold. The rest are used for training. 5 is my assessment fold. The rest are used for training. As a consequence, for my model 1, I get 5 different accuracies from here, from here, from here, from here, and from here. So what is the accuracy of my model 1? Well, I just take the mean. And now I have the accuracy for model 1. Now I go to model 2. I ran it without the first fold. I make the second fold assessment fold, the third one, the fourth one, and the fifth one. I take the average from all these 5 folds, and I have the average accuracy of model 2. I can already see if model 1 is better or model 2 is better, but I just wait. I do the same thing for model 3 here. I get 5 results based on the 5 assessment folds. Take the average. Now I have the mean for model 3. Do the same thing for model 4. And I have the average for model 4. You can already see that this is kind of time consuming. Think about it. I have 4 models here. Each model has to go through 5, has to be trained 5 times for each of the scenarios here, for these ones. So that is 4 times 5. These are already 20 runs. Then think that each random forest has 200 trees. So a total of 20 times 200, 40,000 trees need to be trained here. You will see This goes surprisingly fast. So, but where are we? We have the mean here for the fifth model from these 5 folds. So we know the average performance, the average accuracy of our model 4. We have that for model 1, 2, and 3. So only what we have to do is compare the means of all 4 models and find out which is the winner. In this case, we say the winner is model 2. The parameters for model 2 are, make sure we don't keep splitting when we have 10 or less, when we have 10 or the other way around, only allow further splitting if we have more than 10 records in our node. Use 3 variables out of the 5 at each split. This is our best model. And that is the model that we use for prediction. So what is missing now is we have to do the same thing in R and let it run. We are back to R. I hope you can see it. And I load the new R file here, which is almost the same than the one before. And I will point out the differences. What is the same is I load tidy models, I load the tidyverse, I use the same data, I use the same split in training data and testing data. I assign factors to survived and to the variable sex. Did that before, no change here. I generate my training data as before. I generate my test data as before. Okay. Here I make the first step, I create my folds. Remember, I had 5 folds, so V for the folds is 5. I create them from the training data. I do that only once. And I ask R to make sure that each fold has approximately the same number of survivors. That makes everything a little bit more balanced. And this information, which data record goes in which fold, in which of the folds 1, 2, 3, 4, 5, is saved in the variable CV folds. Again, the variable, you can call it whatever you want. I run my more random forest model again with 2 modifications. I set the parameter trees to 200. I think the default was 200, but I set it to 200 here. And the number of trials of variables, I could set it to 2 or 3, but I want this to be tuned. So I just put this placeholder here, which basically means I don't know yet. Find out. The same with the minimum amount of records that need to be in each of the nodes that allow me to split further. I leave that open. I set the engine to RandomForest. And very important is, before we had the fit command here. Well, we can't run the RandomForest at this point because we haven't set what these tuning parameters are. They are just like, okay, we have placeholders here. So if you put the fit command here, you will get an error message. That's why I deleted it. Okay. I execute this command so you can see what it does, and then I explain it to you. It basically creates my scenarios. My first model is 2 variables, 10 records. Second model is 3 variables, 10 records. Then again, 2 variables, but now 30 records. 3 variables, but now 30 records. These are exactly the parameters for all of my 4 variables. And that's pretty much the only thing you have to know, except I don't have to do that manually. This command helps me with it. It says mtry is 1 parameter, and that should go from 2 to 3. mmin is the second one, it should go from 10 to 30. And I wanted 2 values for the first one, which is obviously 2 and 3. If I would set that to 3, I would get 1 in the middle. And I want to get 2 from this one, which is 10 to 30. So I executed already. I executed again. And now I do my tuning here. And since this takes a while, I just do it. And then I see it entertains us because I set verbose equals true. I could set it to false and it would run silently. I like to run it, even if it runs a tiny little bit slower with some feedback, and it's done already. Remember, 40,000 trees had to be calculated. It's done. So I want to collect my results, basically calculating my means, because what I have now, for each of the 4 models, I have 5 different runs, and I want to calculate the average out of these 5 runs, like we did in the PowerPoints. I can see it here. Here's my model 1, here's my model 2, model 3, model 4. The metrics I used was accuracy, it was a classification problem, and here is the mean that I got from the 5 folds. And you can already see which model is best. The best model is actually model 3 with an accuracy of 0.817 and with mtray of 3 and min n of 10. I could do that by hand, but R does it for me. So what are my best parameters? I select them from my results here. And here we go. 3 variables with 10 minimum requirement for another split. So the only thing what I have to do is I have to run the model. And the nice thing is, instead of starting over now, there is a command that says finalize model. What it basically does, it uses my model here and finalizes it, and finalizes is puts in what is missing. What is missing in my module is, here I have a placeholder, and here I have a placeholder. So I need numbers for that, and that's what finalize model does for me. It takes a model and puts the best parameters for these 2 values, that one that I just found. And now my model is finished. And because it's now finished, I can actually fit it. And here comes my fit command again. Formula equals survived. And I think because it's the first argument, I could even leave it out. So you can write formula, or you can write it like this. Survived, here's the separator, use all variables in the data set. Which data set? The training data set. Run my model. Takes only a second or so, it's done. Now I can run my confusion matrix. There is no change, so I don't have to explain it. Here's my confusion matrix. Pretty good. And what is my accuracy? Great accuracy again. 85%. So my best model has an accuracy of 85% based on the test data. The other accuracies I saw before were based on my folds from the training data. So the real test here, how good my model is based on the test data. One comment here, you might remember from our first run that the accuracy was actually better. How could that be? Well, the explanation is simple. The standard RandomForest does some tuning in the background. And this some tuning, what it does in the background, the standard one, is not that easy to beat. But if you really want to know what you're doing, it is always better to tune it yourself. Then you know exactly what you're doing. Thank you for tuning into this class. I wish all of you a nice day and see you next time. Bye-bye.